All right, we're continuing with the curve sketching example problem videos. This is the 9th of these example problems. In this video, we're going to sketch the function y is equal to the natural log of sine of x. Okay, step 1, the domain. So what is the domain of sine of x? It's all real numbers. Okay, but it's really more of we need to look at what's the range of sine of x. The range of sine of x is 1 to minus 1, including 1 and minus 1. All right, so from that range, what portion of that range is included in the range of the natural log of x? So what's the range of the natural log of x? So a logarithm. What's the range of log of x? Or no, the domain of log of x, I'm sorry. So we want to know what portion of the range of sine of x, which is 1 minus 1 inclusive, is included in the domain of natural log of x. What is the domain of a logarithm? It's 0 to infinity, not including 0. So what that means is that the portion of the range of sine of x that is going to be part of the domain here is 0 to 1 inclusive, including 1. Not including 0, including 1. So what we need to figure out is what x values for input into sine of x correspond to this here. Okay, so if we think about the unit circle, so you've got sine on the y-axis, cosine on the horizontal, 0 to 1 when it comes to sine of x. You have sine of x is 0 when x is equal to 0, and then when x is equal to pi over 2, sine of x is equal to 1. When x is equal to pi, sine of x goes back to 0. And then when you keep going, you go into the sine of x becomes negative. All of this is definitely not part of what we can input into the natural log, right? We can input a negative number. And so there you go. So we can see that the x values that correspond to 0 to 1 are 0 to pi, here to here. Here's the range, right? Here's that 0 to 1. But the x values that correspond to this are 0 to pi. So the domain we would say is 0 to pi, not including the endpoints, because the endpoints correspond to sine of x is equal to 0. Okay, but we know that with the sine function, it's not just 0 to pi. It can be, so it's 0 to pi, and then also 2 pi to 3 pi, and then 4 pi to 5 pi, or negative 2 pi to negative pi, right? Or negative 4 pi to negative 3 pi. Any of those inputs would give us outputs. If we put in sine of it would be 4 pi to 5 pi. If we put in sine of 4.5 pi, we get an output here into this. Natural log of sine of x, if we input x is equal to 4.5 pi, we get an output. So really, technically, if we want to give the exact precise domain here, what it is it's 2n pi and then 2n minus 1 pi, not including the endpoints. So n is equal to 0, you get 0 here. And then n is equal to 0, you get, no, 2n plus 1. Plus 1. N is equal to 0, here you get pi. So you have 0 and pi. N is equal to 1, you get 2 pi. Here, that's 3 pi. What about n is equal to minus 1? You get minus 2 pi, and then here you get minus pi. You see? So that's the domain. And usually, we're going to see that this is periodic, so we're only going to sketch one period. And usually, I just put the domain for one period of the domain, but I'm going to go ahead and leave this here. The domain as the general domain. Okay, what about the range? We'll come back to the range once we draw the function. All right. Now, let's do the period. Let's do symmetry. Let's come to the periodic symmetry. Let's do that first, okay? So, is there a number p such that y of x plus p is equal to y of x? Okay, so we know that the sine function has period 2 pi. So perhaps I've input there's the equation. So perhaps the full function will have period 2 pi as well, and it does. Okay, so the period is 2 pi. It's going to have a repeating pattern every 2 pi. This exact same pattern is going to repeat all the way from plus infinity to all the way to positive infinity and all the way to negative infinity. Okay, so this is periodic with p is equal to 2 pi. All right, so we're going to draw one period. Okay, and in fact, actually, let's redo the domain here based on, we're going to draw one period, so let's redo the domain because this will help to illustrate something. And so you might be saying, okay, so the period's 2 pi, so we're going to do the domain 0 to 2 pi. Well, no, we just talked about how if we're just thinking about one rotation of the unit circle, one rotation, okay, a single rotation. We just talked about how it's only, the domain is only for 0 to pi, not 0 to 2 pi. But the period is 2 pi. So isn't that's kind of weird? If we're only doing we're only doing one period. We're not going more than one rotation around the unit circle. And we know nothing in this range is part of the domain. Nothing in here is part of the domain. So that's saying that the domain here, if we're thinking about one period, the domain is going to be 0 to pi. And that's correct. So but the period is 2 pi. The idea is what's going to happen is you're going to have, so if this is pi and this is, or if this is minus pi and this is pi, so all of this is 2 pi, only in one half of this are we going to have a function, and the other half is going to be empty. And then when we start up again at the next period, that function is going to repeat. That's the idea. But this is not part of the domain. Nothing in these regions are part of the domain. Nothing on these halves of the function of the period are part of the domain. You see? That's the idea. The domain, when you give a domain, remember the definition of domain. Domain is you're specifying what values or what are the values to where if I input them into the function, I will get an output. If there's a value that you input into the function and you get like does not exist or undefined or whatever, that's not part of the domain. So none of this is part of the domain. You don't get a value if you input anything in here. Okay? That's why the domain is, it's in general, it's 0 to pi, 2 pi to 3 pi, 4 pi to 5 pi. You're not including all those, the under half of the unit circle on any given rotation. Okay, let's do the intercepts now. And so actually what I'll do is we'll say, so minus 10 to 10, and then we'll do 6 to minus 6. That should give us a good view of this. Okay, now so the intercepts. So y-intercepts, we set x equal to 0, but that's not a part of, see, the domain here is going to be 0 to pi. So 1, 2, 3, about in this region here. And so it's confusing. It's confusing. This is the only region where we're going to be drawing the function in this x region, but I'm leaving space here so we can see the full period, see the full 2 pi, and maybe see it. I can put in the start of another period. Okay, so but it's confusing. So the domain here is just 0 to 1, 2, 3, about this region, and so we can't have. There's not going to be any y-intercept because to have a y-intercept, x is equal to 0, and we're not defined. That's not part of the domain. X is equal to 0 is not part of the domain. So, okay, what about the x-intercepts? So we set y equal to 0 and solve for x. Okay, so algebra. Okay. Take the equation equal to 0, solve for x. Okay, so 2 pi n plus pi over 2. So when n is equal to 0, we get pi over 2. So pi over 2 for sure. What, is there another one? N is equal to 1, you get 2 pi plus pi over 2. Nope. What about minus 1? You get minus 2 pi plus pi over 2. That's still less than minus pi. So because that's the period we're going to be viewing the period from minus pi to pi. So, but we know that there's, from minus pi to 0, there's not going to be anything, but that's the period we're looking at. So this for n is equal to minus 1, you get minus 2 pi plus pi over 2. That's like minus 3 pi over 2. That's outside of what our one period. N is equal to 0, you get pi over 2. Yep. N is equal to 1, you get 3 pi over 2. That's outside of the period we're looking at. So x is equal to pi over 2. And so we can see what point is this. So pi over 2, and then e with x equal to pi over 2 is 0. Yeah, well, of course, that's an x-intercept. Yeah. Okay, so let's plot this. So, okay, pi over 2 is like 1.6. So 1, 2, 1.5, so about right there. There's pi over 2. Okay, now let's test for symmetry outside of periodic symmetry. So what about an even function? Okay, so substitute x for minus x. And what does this result in? Okay, so natural log of minus sine of x. This is not equal to y of x. Okay, what about an odd function? Minus y of x is equal to minus natural log of sine of x. And I believe that's not anything either. No, so that's not equal to y of minus x. So just periodic. Okay. Okay, next, endpoint behavior. To check endpoint behavior, you take the limit as the function approaches each of the endpoints of the domain. So what is the limit as x approaches 0 from the right of natural log of sine of x? Okay. So we take the limit. Well, we'll need to do, okay, the limit of the equation with respect to x approaching 0 from the positive direction, negative infinity. Okay. Okay, now what is the limit as x approaches pi from the left of natural log of sine of x? Right, so as x approaches pi, negative infinity. Okay. So these, we're approaching a single x value, a constant x value, and then we're going to positive or negative infinity. So that's vertical asymptote behavior. These are vertical asymptotes. They're technically vertical asymptotes. I put them in different categories when we're doing curve sketching like this because they're associated with the endpoints. And so just note that these are associated with endpoints of the domain that we're drawing. But these are vertical asymptotes. So the origin is a vertical asymptote and pi is a vertical asymptote. So 1, 2, 3. So right to the opposite side here of 3. That's a vertical asymptote. And x is equal to 0. Okay. Next, let's get the critical points. Okay, so we'll start with the first derivative. So take the derivative with respect to x. Okay, so there's nowhere where this is going to be equal to 0, where the first derivative is going to equal to 0. But what about, where does tangent x equal 0? Well, okay, the unit circle, you think it's sine of x divided by tangent of x, or cosine of x. So when x is equal to 0, x is equal to 0 is going to be well, no, that's not going to be a critical point because that's at an endpoint. So we're just looking away from the endpoint. So is there anywhere else? Well, actually, no, I take it back. This could potentially be equal. Let's solve for where this equals 0, because you could convert this to like cosine of x over sine of x. So let's solve for where this equals 0 for x. Okay, yeah, so it can equal 0, and it would equal 0. So let's put n is equal to 0. You get pi over 2. So pi over 2. The first derivative equals 0 at pi over 2. And we know pi over 2 is a x-intercept. Okay, what about when n is equal to negative 1? That's negative 3 pi over 2. What about 1? That's 3 pi over 2. So, okay. Now, can tangent of x ever be equal to 0? I think it's only got 0 and pi. So that's not relevant to this here. So tangent of x equals 0 for x. Yeah. 0, pi, 2 pi, etc. So this is the only point here. Pi over 2, 0. At this point, the first derivative is going to be equal to 0. You have a horizontal slope. Okay, what about the second derivative? All right, so dx squared. Okay, is there anywhere where this equals 0? No. Okay, is there anywhere where sine of x squared equals 0, so the second derivative wouldn't exist? Zero, pi, 2 pi, so just from 0 to pi, so no. So there's none here, none. Okay, now let's get the intervals of the increasing and decreasing intervals. So we've got 0 and then pi over 2, and then pi is the end of the domain. So we're really just looking at these two regions here. So, okay. Take d dx. All right. So we do this with x equal to, let's do 1. And what is that? Is that positive or negative? That is positive, so increasing here. Okay. Now let's do this again with x is equal to 2. Negative, so decreasing. Okay. And it's not defined in these regions until you keep going in the period starts again. at 2 pi and at, it would be negative pi, right? Because you go from negative pi to pi as one period. Okay. What about when you think about the second derivative? Well, there can't be any change in the second derivative. And so all we're going to do is just say from 0 to pi, there's going to be one concavity. Okay, so x is equal to 2. Concave down. Okay, so that's it. Okay, inflection points. There's no inflection points because there's no critical points with respect to the second derivative. What about local maxes and mins? Well, this function is going to be continuous everywhere within its domain. And so with that, we can use the first derivative test, if applicable, at a critical point to see if we have a local max or min. Here's the critical point. We go from increasing to decreasing, so this is going to be a local max. Okay, so we know we're going to have like a behavior like this, with its slope 0 here. Okay, so now we can sketch the curve, and what's going to happen is we don't have any. We have one critical point, and then everywhere else, there's no special points. There's no inflection points. There's no other local maxes or mins. So we know we're just going to do this. And that's it. And so okay, the limit as x approaches 0 from the right, negative infinity. Pi from the left, negative infinity. Local max here at x is equal to pi over 2. Increasing and then decreasing past pi over 2. Concave down the whole time. So there you go. The x-intercepts, there's only one x-intercept, no y-intercepts. There's the x-intercept, so that's it, right? So, but now just to show you, so let's draw the full period here. So this goes from, this is pi, let's go to minus pi. So 1, 2, 3, there's about 3.14, negative 3.14. Okay, so there's the full period, and it's undefined in this region, but this is periodic in the sense that, you know, if you start up a new period, you're going to get, you know, this, right? If you came over here, you would do the next thing, right? It would be, you'd have these blocks of 2 pi with one interval of the pi, you've got the function, and the other interval is empty. That's how it's periodic. This is one period. This empty pi region followed by this graph here in the other pi region. Here's another period. Empty pi region followed by this graph. So that's the graph. Okay, so what's the range? Before we end, what's the range? The range is going to be 0 to negative infinity. You can input any value within the domain you want. You'll be able to get values from 0 to negative infinity, including 0, but nothing else.